Hi, Module 2 or Module 3, Part 2. And you'll notice that I skipped a slide or two, and it's just talking about the net balancing of the amount of sunlight that comes into the atmosphere. And this is an image that's showing the same thing, net radiation and absorption of that energy over the surface of the Earth. And surface atmospheric radiation exchange is talking about how we can account for that energy within the atmosphere. This is just talking about the absorptive properties of certain materials, specifically greenhouse gases. Water, CO2, which are two of the primary forms of greenhouse gas, are highly reactive and absorb heat energy readily. So when hit with wavelengths of light that are in the spectrum of visible and thermal infrareds, they have a tendency to absorb them and radiate them out later as those thermal infrareds. We've already talked about conduction and convection. But really quickly, convection within the atmosphere itself, so within its standard composition of nitrogen, oxygen, a little bit of everything else, you can see a natural cycling based on that density, where the warm atmospheric material will rise. Once it cools off, it will sink back down, right? So it can sort itself. This convective force can cause a variation between what we call high and low pressure systems. And so right here, I can see an area where the air is rising, which is leaving space down below, making this area having a set of pressure which is kind of in its high forms, right? And so we're having here, and so it's rising up above on the high, and it's sinking down, creating an area where the pressure is incoming, and then it's rushing because everything's so jam-packed in the location where the air is incoming. It's rushing towards the area where there is space available, and that creates things like wind force. But there will be an entire chapter where I will go into this in great detail. We're just touching on topics. Sensible heat is our personal organ ability to feel the molecule movement. So how far and fast are all of this fluid material that's around us moving? The more energy the molecule has, the warmer the temperature I will sense, right? So that's my sensory on that sense. Latent heat is a different concept based on the same sort of things, but latent heat is the heat that can be either absorbed or released based on phase change. And this is incredibly important because it determines how clouds will interact and heat themselves so that they'll stay warmer throughout. And this has to do with latent heat process. So work with me here. If a material is, I don't like this image. Where's the good image? Oh, do I now have the good image? I'm sorry. So if a material happens to be a solid material, I know these are just measurements, but bear with me. If the material happens to be a solid material, the molecules are moving very, very slowly, right? So they're vibrating only so slowly. And in order to get them to change phase, I have to warm them up and get them to move more quickly. So in order to do that, it means that it is doing a latent heat exchange of absorbing energy. So I'm doing energy absorption to go from solid to liquid. Now, to get from liquid all the way up to gas, I will have to absorb energy yet again. So one form of latent heat is to absorb energy. Now, where am I getting that energy from? From all the stuff around that object. So if it's in the atmosphere, I'm talking about a water droplet. In order for that water droplet to go from its liquid state to its gas state, it's actually taking energy from the air around it, all the molecules around it, meaning that while the water droplet is gaining energy and more or less warming up, the air around it is losing that energy and it's actually cooling off. And this is a very key concept, so please take your time, wrap your head around this latent heat. On the other hand, to go in the opposite direction, where I'm going to go from gas down to solids, I have to lose that energy. If I'm a gas molecule, I'm moving very far and fast, I have to release that energy, and I will release it to the air around me, and that will actually heat up the air around me as I begin to cool off and slow down. And then I will finally reach the right temperatures where I will begin to act like a liquid, In order to go from a liquid down to the solid, I will again have to release that heat energy, and that will cool me off, and I will begin to move slower and become less active down to a solid phase, and the air around me will actually warm up in exchange. So that is my latent heat. Energy transfer based on the actual latitude. So looking at the Earth as a globe. We already talked about seasonality and direct sunlight hitting the Earth and how certain times of year receive the perfect 90-degree angle, so the greatest amount of sunlight, and how other times of year it's reduced. And that's because the Earth is naturally tilted on its axis of rotation at 23.5 degrees. And that means that when the sun is facing most directly the northern hemisphere, it will actually be touching a 90-degree angle at 23.5 degrees north. On the other hand, when the Earth's natural rotational axis is tilting the northern hemisphere away from the sun, and it's hitting the southern hemisphere more directly, I will receive a 90-degree angle on my sun, light hitting the Earth's surface, at 23.5 degrees south. That also means that 2 times a year, I will hit a point where it's hitting 90 degrees exactly at the side of my rotational angle, right? And that means it's hitting the equator on my latitude of 0. Speaking of some of these effects, we can talk about greenhouse gas effect and the ability of energy to now absorb sunlight and then trap it in. And this is the greenhouse gas effect. Now, before we begin talking about climate change and greenhouse gases in regards to climate change, one of the things we have to keep in mind that there is a natural cycle on the Earth's surface, and that consists of this unusually high number of greenhouse gases that happen to be within our stratosphere. And that stratosphere acts as a nice down comforter on the Earth's surface here, and it tucks us in nice and warm and keeps us at a nice, comfortable temperature where we're not being irradiated by ultraviolet light because it's being blocked out by our ozone layer. And at the same time, it's absorbing heat energy and radiating it out as thermal infrareds, which is keeping our planet from becoming an atmosphereless, frozen planet. And so it's kind of an important key function to maintaining the Earth as it stands. This brings us to global temperature distribution. We consider places that are above about 40 degrees north latitude to the North Pole, 90 degrees north latitude. We consider that a deficit of energy zone. Same thing on the opposite side. So if I take the southern hemisphere and I go from about 40 degrees south latitude and I go to the 90 degree South Pole, that area down there between those latitudes, I consider a deficit area, which means that I have a deficit from 40 to 90 south and 40 to 90 north. I consider myself having energy surplus in the regions between 40 degrees north latitude to 40 degrees south latitude. So that's my surplus zone, which means that I have a variable in my heating differentials. And that also means that there is a lot of weather mixture or a lot of activity of atmosphere rushing from zones of surplus to zones of deficit. And that's one of the key things. As much as weather can be an interruptive property of the Earth's surface, it is absolutely key in exchanging that energy over the entire planet. So I'm creating an energy balance. I'm creating that net zero. And so weather is the instrumental process that makes our planet a livable one. So just talking about latitudes, variations in northern and southern hemispheres, and here we go. Here you can see January surface temperatures. This is in Celsius because that's good math. And you can see right here, there's a variation in the variable temperatures. And if you look closely, you'll see that the January months, the 0 mark is way up here. In the summer months, the freezing mark in our summer months, in July, the freezing mark is way down here, and vice versa. And I'll pick up talking a little bit more about this in a next video.